Okay, we can start this afternoon session of this webinar. My name is Aljaž Pogacnik. Today I will be giving the webinar with the title Hobbing and Rollout Calculation. The webinar is held in a listen-only mode, so if you have any questions, you can use the question section of the GoToMeeting. At the end, we will answer some questions, and if your question will not be answered, then you will receive an answer via email. I will deactivate my camera just in case we have some problems with the connection. And we can start. So, as I said, the title is Hobbing and Rollout Calculation in KISSsoft. First, a short overview of the presentation, of the content. We will first check the tool types we have in KISSsoft. We have 4 different options to define a tool, let's say. We will check the definition of the pre-finishing operation. This is something that has changed in the 2025 version compared to the older versions. We will check the rollout analysis calculation. This is also something that was added in the 25 version. We will check that how the hobbing cutters can be defined in tab-tooth form, how to define hobbing cutters with short and long lead. We will have a brief check about the hobbing process module, also something new for the 25 version. And at the end, I will do a short example calculation, doing all the steps we will check today. So from entering the gear data, entering the tool data, and then also the rollout analysis. So tool types in KISSsoft, as you see here on the right picture, we have 4 different options to define tool geometry, let's say. We have also 3 different options to define the geometry plus the constructed involute. We will today focus on the hobbing, but just a short overview. So if we select a reference profile of a gear, basically the gear is defined directly to the reference profile. And then on top of it, the tool is calculated and used for the geometry generation. Then we have pinion type cutter, or also a shaper cutter. In this case, the gear is defined through the reference profile of a hobbing cutter. We have a scheme here on the right side, and beside the tool geometry, also the tooth number, of course, and the profile shift have an effect on the final tooth form. Now to the hobbing cutter definition. So in this case, the gear is defined through the rect type tool, and the reference profile of the tool is something that we enter in the user interface. So it has a protuberance part, it has, of course, the height, and it also has the chamfer flank part. Of course, we can use 2 different tools. In this case, we can have a non-topping tool and a topping tool. So for the non-topping tool, the addendum of the gear itself has to be bigger than the addendum of the tool, which is this equation here. And for a topping tool, basically the addendum of the tool is also doing the tip diameter of the gear. What parameters do we have for the hobbing cutter and what inputs are available? So we have addendum and addendum height, HAP0 and HFP0. So we have here 2.2 and 2.8. Those would be the values from the reference line, 2.2 and 2.8. We have the protuberance inputs, which would be the protuberance height and also the protuberance angle. That's something we see here, so 14 degrees. And the height is coming, it's coming from the top, 1.467 in this case. We can have the definition of the chamfer flank, also semi-topping. How we call it is HFFP0 and alpha KP0. So those would be the angle here and the height of the chamfer flank. This, again, the reference is in this case from the reference line. We have 2 radii. We have the tip radius, and also the root radius. And we have also the tooth thickness factor SP0. As I said before, we have an option to define if the tool we are using is a topping tool or a non-topping tool. In the reference profile tab, we have several convert and size buttons available. What those functionality offers is that we can calculate some parameters of the tool based on different inputs like tip and root diameter, tip and root form diameters. And in these conversion buttons, we have different inputs for pre-machining and finishing, or pre-finishing and finishing. And also we have options to define diameters for minimum and maximum tooth thickness. Hobbing cutters can also be selected from a database, so we have option to have as an own input, so you can define your own geometry by simply inputting the data in the user interface, or there is an option to select the Hobbing cutter from a database. Currently, we have two databases inside, DIN 3972 part 3, let's say, and 3972 part 4. You can also add your own tools. You can also create your own databases if you want. I will show you how to do that. And the parameters of the Hobbing cutter are shown in the table, and also there is an option to restrict the selection of a Hobbing cutter to fit the existing normal module and pressure angle. How this database of Hobbing cutters can be used is also we can use it together with the fine sizing functionality. I will show you that. So if we select here a Hobbing cutter, we have here an option to select it from the a database. In this case, this is limited to 6, the module 6 and pressure angle of 20. If we have an input, of course, the input fields is something we can change. And also, if we click on this database button, we can add this tool to the existing database, and then this tool is available for us for selection in the database we've saved it to. About the fine sizing functionality, so in conditions 2, there is an option here to select the list of Hobbing cutters for gear 1 and gear 2. And this, of course, can be your own database of tools. And if you select this, then the fine sizing will run through all the tools and calculate the possible solutions using your own tool geometries. Moving on to the definition of the pre-finishing operation. As I've said before, the definition of the pre-finishing operation has changed in 2025 release. However, if you have old files, the geometry of the old files, the grinding stock and the tolerance of the old files is updated to the new inputs, the Q-min and TSNV. The new values are recalculated, and we are keeping the same pre-finishing tooth thicknesses in the old and in the new release. So we adjust the minimum finishing stock and pre-machining tooth thickness tolerance so that we have the same pre-finishing geometry in both files. So the definition of minimum finishing stock is shown in this picture below. So we have the minimum finishing geometry and the maximum finishing geometry in gray, and then we have with green the minimum pre-finish geometry, and with black the maximum pre-finish geometry. And the minimum finishing stock is the distance between the maximum finishing and the minimum pre-finishing. So the distance between gray and green is, in this case, our Q-min, and this is 0.15 as we have entered here. If we check the picture from the new ISO 21771, we see that this Q-min is the distance between the maximum finish, that would be here, this line, and the minimum pre-finish, which is this line. Of course, we also need to define the tooth thickness tolerance of the pre-finish. So in our case, we have a definition of TSNV as an input in the calculation. There is also a convert button available for the minimum finishing stock, and there you have three different options. You can calculate Q-min and TSNV from base tangent length, measurement over balls and pins, and the profile shift. So this is very similar to defining a tooth thickness allowance. There is also a very similar dialog available there. Something about the grinding notch. So on the left side here we have a tool without the grinding notch, and on the right side we have a tool with, we have a tool without protuberance, and on the right side we have a tool with protuberance, and on top we have the resulting tooth forms. Of course, for the two-stage operations, meaning we have a pre-finishing operation and a finishing grinding, let's say, if we don't have a protuberance of the tool, we can end up with a grinding notch, as we see here on the bottom. To avoid the grinding notch, we can have a protuberance tool, and with the protuberance tool, we basically remove some material in the root fillet area, that we have a smooth transition between the final involute and the fillet area. So grinding notch is the result of manufacturing operation, can increase or decrease the root stresses. It's not always that the grinding notch is making things worse. In some designs we see is that the grinding notch is kept. If you have a stable manufacturing process, then having a grinding notch is nothing really worrying, so it can be a normal thing. But in majority of cases, a protuberance tool is used to try to eliminate this grinding notch here in the tooth root area. So protuberance tools, what they do is they increase the clearance in this fillet area, they remove the grinding notch, and in some cases can also lead to a better stress distribution in the tooth root area. Now to the rollout analysis. So we have defined our pre-finishing geometry. We know what's the minimum grinding stock. With this, our finished gear geometry is defined, and we can then do additional rollout analysis. So what's the purpose of rollout analysis? Basically, the rollout analysis simulates the effect of stock tolerances, gear tolerances, and also hop tolerances on the final tooth form. So additionally, what the rollout does is it also considers the hop tolerances and calculates different diameters, as we will see later on. It's based on worst case tolerance combinations. I have a table later on to show you how we combine tolerances according to some Gleason recommendations, let's say. This rollout helps the users to check if the gear still meets the requirements, considering also these manufacturing variations, and it's quite useful at the relatively early design stage to see or to understand what's the effect of tolerances also on the final design. We are calculating three different conditions. We have minimum stock, maximum stock, and defined stock, sometimes called also the nominal stock, which is a stock which is somewhere in the middle between minimum and maximum stock. So as I've said before, this is considering also the tool tolerances. So in the user interface, you have an option to select cutter tolerance class according to Gleason cutting tools. I think we have 5 different classes going from AA to D. And the user interface, which has 3 columns. The first one is the value of so the values are relatively small because this is a table in inches. So there is a value of the tool parameter, and then we have also a definition of the upper and lower allowance. Manual inputs are not possible for all. Depending on the tool geometry, we can define inputs for the addendum, for the tip radius, for the root radius, protuberance height, protuberance amount, root form height, and also for the tooth thickness reference line. Additional settings are possible for the graphic. What we see here are tip form, tip diameter, tip form diameter. We have root form diameter and root diameter. Those are all coming from the basic KISSsoft calculation. Also, the pre-finishing and finishing manufacturing profile shifts are coming from the KISSsoft calculation. The users can change it if they want. Otherwise, we take the default KISSsoft units and show it in the graphic, as you will see later on. Of course, with checkboxes, the users can override all the values. About the combinations that are taken for certain calculation conditions. So we have here two tables. The first is for the hops, where we have also pre-finishing. So we have pre-finishing and finishing operation. And maximum stock in this case would mean that we have the smallest tooth thickness on the finish tooth. We have the highest tooth thickness on the pre-finish. This will give us our maximum stock conditions. To consider this, we also take the maximum hop tooth thickness. We take the minimum tip radius. We take the minimum protuberance amount. And then we have here, based if it's a topping tool or non-topping tool, also a different combination of tolerances. For the minimum stock, this means that we have the finishing tool at the highest tooth thickness, so we have high limit here. Pre-finishing would be at its smallest, so we have the low limit there, means that this will result in the smallest possible grinding stock. And then the tooth thickness of the hop is also at its low limit. The radius and protuberance amount are at the high limit. And then again, depending on if it's topping or non-topping tool, we have different combination of tolerances. If we use the hop without the pre-finishing operation, so we only use the one step to cut the gears, then we're not checking, of course, the maximum and minimum stock anymore. We are checking the maximum and minimum diameter. Again, there are certain conditions that are used here. Like for the maximum diameter, we have the high limit for the tooth thickness of the gear. For the maximum tooth thickness of the hop, the tip radius is at its highest, and vice versa. For the minimum diameter, we have the low limit for the gear tooth thickness for the hop tooth thickness and for the tip radius. And then based if it's a topping or non-topping tool, we have different combinations of tolerances. So those are conditions for the worst cases, which are then also used in the rollout analysis. So what we do in the calculation is we generate for each condition, so for the maximum, minimum, and nominal, we calculate different tooth forms. So basically we do three combinations or three different calculations, one for each stock condition. So we define the hobbing cutter based on the tolerance conditions we saw before. We generate the pre-finishing tooth form, which would be the blue one. We add a theoretical involute for the grinding, and then we are checking different diameters, as we will see in the graphic, to see if our manufactured gear still meets the desired requirements from the original design. So we calculate several intersection points, like for the tip and root form diameters. We can calculate the maximum undercut. We can calculate the re-entry diameter. And this calculation is currently supporting only the hobbing cutters. And we are planning to do also a short long lead hobbing cutters for the 26 release. So as I've said, one hob is calculated for each stock condition. Based on this Gleason tolerance matrix, we then have 3 different combinations of results. And what we're calculating is displayed here. So we calculate the tip form diameters of finishing and pre-finishing. We have the root form diameters of finishing and pre-finishing, max undercut. Of course, we're also checking the root diameters. And in case we have a topping tool, we are also checking if the tip diameter falls within the specification. So we also have some nice graphics showing us all 3 stock conditions at the same graphic, which we can activate or deactivate. This is located under Geometry 2D, item rollout. We can additionally display some theoretical diameters for additional checks. And these graphics really visually represent how the tooth form will be at its worst conditions. These are those 3 graphics separated side by side. So we have the minimum stock here. We can see that the protuberance amount is sufficient. We have some free space here for the grinding tool to exit. We have the defined stock, which would be somewhere in the middle between minimum and maximum stock. You see, we're just touching the protuberance part or the root fillet area with our grinding. So this is right on the edge. And then for the maximum stock, in this case, we don't have enough protuberance. So in this case, if we would exit with the grinding tool, we would end up with a grinding notch. So what we discussed until now is how to define the hobbing cutter in tap reference profile. Additionally, we can define a hobbing cutter also in tap tooth form. We can have here several different manufacturing steps. We can add them one after the other. We can also have several cutter steps or hobbing cutting steps here, and they're completely independent. What we see here is the user interface from the tap tooth form. The user interface is the same as we saw before. Additionally, what we select here is also the manufacturing profile shift, but also we can have here different normal module compared to our original design. So this manufacturing step in the tap tooth form allows us to have long and short lead tools used for the generation of the tooth form. Briefly about the long and short lead tools. So theoretically, 2 tools with different pressure angle and normal module can produce the same involute. In order to do that, they need to have the same normal base pitch, and as a result, the involute part or the tooth thickness is the same. It will just have a different root form diameter, as we will see on the next slide. When are the long or short lead tools used? They can be used to improve the fillet stress distribution. They can be used to optimize the hob lifetime. And if we only have finishing operation with the hob, it can also be improved. It can also be used to improve the quality of the produced gear. Like I said, if we're not grinding the gear afterwards. So here on the right side, we see 3 different tools. We have our original tool, normal module of 1, pressure angle of 20. We have then 2 modified tools. One has slightly higher pressure angle, one has a slightly lower pressure angle. And as a result, to have the same base pitch, the resulting module is also not identical to 1 anymore. In the example on the left side, we have the 3 different tooth forms generated with the tool we see on the right side. In this case, the base diameter is lower down, and this result, we see that because we have three different tool geometries, we have here the same involute part, so this is not changing, but the root fillet area is changing, and also as a result, the DFF, so the root form diameter, is not the same for all three manufacturing processes. For the middle example, we have even bigger effect. Here we have a combination of a short or long lead tool, plus also the undercutting, because the base diameter in this case is higher up. As I've said, these short long lead tools are currently possible in top tooth form, but we're also actively developing the option to be available also in top reference profile. A few slides about the Hobbing process module before we go to the example calculation. This is also something that was added for the 25 release. This gives us a quick and reliable cost and feasibility checks early in the design stage. The calculation works with the limited inputs and suggests suitable values for missing data. It uses a specific data for machines and tools to plan or to calculate for realistic processes, and it provides some key outputs like the estimated cutting time, the estimated cost, and also the workpiece tool interferences. With this, we can also, again, already during our design stage, move a bit towards also the process of manufacturing the gears afterwards. What inputs are required? So we have option to select the machine type. We have to define the process. We have to, of course, define the tool geometry, not the tools in terms of, also the tools in terms of reference profile, but also other parameters like the length of the tool, number of gashes, and things like that. We also can have some options for the interference checks, and also we have to input some data for the cost calculation. There are some graphics available like the hop and the cutting area, some basic 3D representation of the interference if we have. So this gives just a bit better visual explanation of the process itself. Now we go to the example calculation. I have here a short example that we will now use in KISSsoft to enter. We will just, I made a print screen, so we should have some data available on the display. So I've opened the single gear calculation module. This should be sufficient for now. So we have the normal module, 2.6. We have the tooth number, which would be 63. Here we have the face width, which is 30. And we also have the profile shift, which is in this case minus 0.433. If this option would not be, or if this data would not be available, we have an option to calculate it based on the base tangent length measurement or the balls, or maybe directly from the tooth thicknesses. Additionally, we have to define a helix angle, 22.6, and this is about it in this basic tab. We have to switch in the tab reference profile to a Hobbing cutter, and we will enter some data here. So HAP0 in this case is 4.966. We have to move to the length here because our data in the drawing is in millimeters. So 4.966. We have the tip radius of 0.9. Here we are entering the nominal data, of course, and then later on in the rollout we will enter also the tolerances. The addendum is calculated here below from the total height minus the addendum, which would be 2.769. The root radius is not defined on the on the tool geometry, so we just leave a default value. Protuberance height is defined here, 2.057, and the protuberance angle is 15 degrees. And what we have to do still is the chamfer flank, which has a 45-degree angle here, and the height is 1.806 because this is defined in KISSsoft from the reference line. So 1.806, and the tooth thickness reference line is 4.7240. 4.7240. So we have to add also the tip diameter. So this is still missing. We can, let's do calculation. We can enter it here in the convert button, 198.8 as a nominal value, calculate. We still have to do the active root diameter. This is something we would get from the gear pair calculation, but even in single gears, we can enter it in the basic data under details, DNF. We can enter here 188.6, and also the smallest tolerance minus 0.15. What we still have to do is measurement over the pins. This we can again go to the convert. Our ball diameter is 5, and we enter here 200.469 and 200.357. This is the finishing tooth thickness done, and the only thing we have to do is define the pre-finishing. And also here we have the option, or we have the data available, so 201.1 and 201.3. We calculate, and this would be our basic geometry, basic gear geometry done. If we check the tooth form, we have a protuberance, we have a final tooth form, and what we can do now is we can move now to the rollout calculation. By default, we have here B selected. In our case, we have to go to on input, and we can define then for the row up P0 plus minus 0.75. Root radius is not really used in this case because it's not a topping tool, so we can put it to 0. HPRP0 we can also put to 0 because it's not a topping tool. And for the protuberance amount, we have here those two values. So we have 0 on top and 125 microns as a lower allowance. And for HFF P0, this would be those two tolerances. We have plus and minus 125. And for the tooth thickness, we have upper tolerance of 0 and lower tolerance of 0.125. So those are the basic inputs done. I don't know what's happening with the screen, but anyway, we will simply, okay. So we have the basic inputs done, and we can check the graphics now under Geometry 2D Rollout. We have an option to show just the maximum stock condition. which is something we see here. In this case, we don't have enough protuberance, so if we would grind this one, we would end up with a grinding notch, so that's something we can improve here. If we check minimum stock, we have sufficient protuberance. In this case, we have the still some space for the tool, for the grinding tool to exit during the manufacturing process. What is important here is that we can display the active root diameter, which would be the DNF min, and we have to make sure that our root form diameters for the finishing are always lower than the active root diameters. This means that the meshing will always occur on the involute part. This is true for the minimum stock. We see that active root diameter is higher than the root form diameter, and that's true also for the maximum stock. But in this case, the form is not really calculated because we don't have an intersection. So in this case, we would have to slightly correct our tool geometry or improve the tolerances. So in this case, we have relatively big tolerance field for the pre-machining, so we could put this to slightly stricter tolerances. We can then calculate, check if we have an intersection. It's still not okay, so we can either decrease the root radius of the tool or change the protuberance angle of the tool. In this case, we will change the protuberance angle to 13.5, let's say. We can then calculate, and we have now intersection. What we can check now is, again, if our active root diameter, so the DNF min, is higher than the root form diameter of the final tooth form. So this condition is fulfilled for the maximum stock. Let's check again for the minimum stock. We have here this confirmation also. So the active root diameter is 0.5 millimeter higher than the root form diameter for the finished operation. So this condition is fulfilled. We can also check for the root diameters. So we have this would be the tolerance field for the root diameter. And we see that with our manufacturing process, the actual root diameter is lower than the required tolerances. This would be for the minimum stock. For the maximum stock, this is right on the edge. This actually makes sense because our DF values are coming directly from the KISSsoft calculation, and the basic calculation is not considering any tolerances of the hob. So if we are then additionally considering also the tolerances of the hob, then the range of the DF tolerances becomes wider. And that's something that we can also see in the report, for instance. We have here the root form diameter. And here we have the DF cut, which is also shown here. This is the actual form diameter, sorry, this is the actual root diameter that would be cut with minimum and maximum stock. And we can compare this with the theoretical calculation of the DF. And if this is not matching, we would have to then adjust the tool geometry. But also, in any case, if we use hob tolerances, we would have to extend the range for the root diameter tolerances. Okay, so this was the example, and we can now do the questions. There are a few questions. So the first one, can you output the root stress with and without protuberance automatically with this software? So the root stresses can be calculated either theoretically according to the standard calculation, or you can also calculate the root stresses using FEM calculation in 2D or 3D. And you have to do one calculation at a time, so it's not possible to do with and without at the same time. You have to separate the calculation. And also, currently it's not possible to take the tooth form from the rollout. So it's not possible to take this tooth form and use it in the 2D or 3D FEM calculation. That's something that would have to be further developed. The second question, where can I find the stock conditions? So the stock conditions are, of course, in this presentation, but the stock conditions are will also be available in the Service Pack 2 as a part of the manual. So they will be available in a few weeks' time when the Service Pack 2 will be released. If you need it sooner, you can also write to us and we can send you the manual part for the rollout calculation. So for maximum stock, it's indicated high limit for the Hobb tooth thickness tolerance. Is that correct? So for the maximum stock condition, for the Hobb tooth thickness, the high limit is used. Next question. Is there a way to show the produced root by the grinding wheel versus the line down to the base circle? We need to understand the blend of the grinding wheel and clearances in that location. That would be possible currently without the rollout. If we would go here to manufacturing, for instance, we can here have the two steps. Then, for instance, for the grinding part, we can see the movement of the tool here. As I've said, for the rollout functionality, currently that is not yet done. If you have such a request, you can write to us and we can see if that's something that can be added. Are there any alarm messages on design? Example, short leading of a Hobb by too many degrees, or if we use a non-manufacturable tolerance of Hobb features, too high to make the cutter. We have added several checks for the tolerances if they don't make sense, if they make sense or not for the Service Pack 2. So this will be available for the Service Pack 2. And we currently don't check if it's possible, or we don't show any messages if it's a short lead Hobb possible or not, because currently the rollout is not does not allow it, and we also would need to have some rule of, or some guidelines on what the limits would be. So currently there are no messages shown in that direction, and that's about it. So the questions were answered. Like I said, if you have any further questions, you can simply write to us. We will try to answer. If you have any suggestions for the rollout functionality, you can also write to us. We will appreciate the feedback. and it's also possible to get a test license to test the rollout functionality. There is an additional question: do I need a special license to get the rollout window? Yes, this is under a special license. So you can, if you want to test it, you can receive a test license. Otherwise, you will have to upgrade your license if you want to, let's say, purchase this module. With this, I would like to thank you for your attention. And as I've said, if you have any questions, simply write to us. I wish you a nice evening or a nice remaining of the day if you are in the States. Thank you. Bye.